Hello everyone, today we'll study the general exponential and logarithmic functions. First of all, let me recall the law of logarithms for natural logarithmic functions. Let x and y be positive real numbers, and let r be a rational number. Then we have the following laws. Ln of x times y is the same as Ln of x plus Ln of y. Ln of x over y is the same as Ln of x minus Ln of y. So we can convert replication to addition, convert division to subtraction. The third law says Ln of x to the power r. If r is a rational number, I can bring r to the front. I get r times Ln of x. Those are the laws of logarithms for natural logarithmic functions. Next, let me recall the law of exponents for the natural exponential functions. Let x and y be real numbers, and let r be a rational number. Then we have the following laws. First law says e to the power of x plus y is the same as e to the power of x times e to the power of y. The second law says e to the power of x minus y is the same as e to the power of x over e to the power of y. The third law says e to the power of x raised to the power of r. If r is a rational number, then we can multiply the exponents. We get e to the power of x times r. Next, let me recall the inverse function properties for the natural logarithmic function and the natural exponential function. They are inverse functions of each other. So, by inverse function property, we have ln of e to the power of x equal to x. Inverse function cancel each other out. I get x by itself. Same thing. E to the power of ln of x is x. Inverse function cancel each other out. Get x by itself. So that's what we learned in the previous two classes. Next, let me introduce the general exponential function. First of all, let's consider a positive number a. Let a be a positive real number. Then, by the inverse function property, we know that a can be written as e to the power of ln of a. E and ln are inverse functions of each other. When they are written together, they can cancel. So a can be written as e to the power of ln of a. Next, let r be a rational number. Let r be a rational number. Then a to the power r can be written as e to the power of ln of a raised to power r. I raise both sides to power r. Here, on the right side, if we apply exponential rule number 3, exponential law number 3 says we'll have e raised to some power times r. We'll have e raised to some power times r. When r is a rational number, I can multiply the exponents. Here, since r is a rational number, I can multiply the exponents. So this can be written as e to the power of r times ln of a. This is true for all rational number r. Since this statement is true for all rational number r, so it makes sense to define this statement to be true for all real number r. Next, let me define the general exponential function in the following way. Let a be a positive real number. Let a to the power x be defined as a to the power of x equal to e to the power of x times Ln of a. For all real number x. Then the function f of x equal to a to the power of x is called the general exponential function. Next, based on the definition of the general exponential function, we try to fix a law of logarithm and a law of exponent. Here, the third law of exponents, the third law of logarithm says, if r is a rational number, then Ln of x to the power of r can be written as r times Ln of x. This law is true for all rational number r. However, this law is actually true for all real number r. The third law of exponent says, if r is a rational number, then e to the power of x raised to power r is the same as e to the power of x times r. This law is true for all rational number r. However, this law is actually true for all real number r. Next, we'll prove it. So first of all, let a be a positive number, and let r be a real number. For the third law of logarithm, we try to show that Ln of a to the power r equal to r times Ln of a. For the third law of logarithm, we try to prove this. So, how do we prove it here? Ln of a to the power r. We know that a to the power r, that's the general exponential function. By its definition, a to the power r, for a to the power r, we plug in r for x. So a to the power r is e to the power of r times Ln of a. So here, a to the power r can be written as e to the power of r times Ln of a. Here, r times Ln of a is an exponent of e. Since Ln and e, they are inverse functions of each other, by inverse function property, they can cancel. We get r times Ln of a. So, for any real number r, I can always bring r to the front. So the third law of logarithm is true for all real number r. So, in Law of Logarithm 3, the statement is true for all real number r. Since Ln of a to the power r equal to r times Ln of a for all real numbers, the third law of logarithm is true for all real number r. Not only rational number, is true for all real number r. And similarly, for the third law of exponent, is also true for all real number r. Let x and r be real numbers. We want to prove the third law of exponent. The third law of exponent says e to the power of x raised to power r equal to e to the power of x times r. We try to prove this. So we try to show the left side to the right side. Let's use the third law of logarithm to prove the third law of exponent. So from the left side, if I apply ln, I get ln of e to the power of x raised to power r. Then, by the third law of logarithm, we can bring any real number r to the front. By the third law of logarithm, we can bring any real number r to the front. I get r times ln of e to the power of x. And then, by inverse function properties, ln and e, the inverse function of each other, they get cancelled. We get r times x. So, ln of e to the power x raised to power r equal to r times x. It's the same as x times r. Next, apply function e to both sides. I get e to the power of ln of e to the power of x to the power of r equal to e to the power of sr. Then on the left side, since e and ln are inverse function of each other, by inverse function property they get cancelled. So left side become e to the power of x raised to power r equal to e to the power of sr. So that's the third law of exponent. This statement is true for all real number r, not only rational number r. This statement is true for all real number r. That fixes the third law of logarithm and the third law of exponent. Next, let me introduce the law of exponents for general exponential functions. Let a, b, s, y be real numbers with a positive and b positive. First law says a to the power of s plus y equal to a to the power of x times a to the power of y. Second law says a to the power of s minus y is the same as a to the power of x over a to the power of y. The third law says a to the power of x raised to power of y is a to the power of x times y. And the fourth law says a times b to the power of x equal to a to the power of x times b to the power of x. Let's prove it. We will prove these laws using the law of exponents for natural exponential functions. We'll prove these laws using the law of exponents for natural exponential functions. So first law, how do we prove it? How can we prove a to the power of s plus y equal to a to the power of x times a to the power of y? We know that a to the power of s plus y, by the definition of the general exponential function, we plug in s plus y here. If I plug in s plus y, I get e to the power of s plus y times ln of a. I get e to the power of s plus y times ln of a. Then I can distribute ln of a into the parentheses. I get e to the power of x times ln of a plus y times ln of a. Then by the first law of exponent, for natural exponential functions, we have e to the power of s plus y equal to e to the power of x times e to the power of y. So I can separate these two terms. Write it as e to the power of x times ln of a times e to the power of y times ln of a. Then, by definition of general exponential function, e to the power of x times ln of a, that's a to the power of x. E to the power of y times ln of a, that's a to the power of y. By the definition of general exponential function, we get this. So, a to the power of s plus y equal to a to the power of x times a to the power of y. That completes the proof for the first law. For the second law, we try to prove that a to the power of x minus y equal to a to the power of x over a to the power of y. We know that a to the power of s minus y, by the definition of general exponential function, I plug in s minus y for this x here. I get e to the power of s minus y times ln of a. So by definition of general exponential function, I get e to the power of s minus y times ln of a. Then I can distribute ln of a into the parentheses. I get e to the power of x times ln of a minus y times Ln of a. Next, by the second law of exponents for natural exponential function, we have e to the power of s minus y equal to e to the power of x over e to the power of y. By the second law of exponents for natural exponential function, we have this. So this expression can be rewritten as e to the power of x Ln of a over e to the power of y Ln of a. Next, by the definition of a general exponential function, the numerator e to the power of x times Ln of a, that's a to the power of x. On the bottom, e to the power of y times Ln of a, that's a to the power of y. By the definition of a general exponential function, we get this. That's the proof of the second law. For the third law, we try to prove that a to the power of x raised to the power of y is a to the power of x times y. So for a to the power of x itself, by the definition of general exponential function, a to the power of x can be written as e to the power of x times Ln of a. Next, I can raise both sides to power y. I get a to the power of x raised to the power of y equal to e to the power of Ln of a raised to the power of y. Then, by the third law of natural exponential function, we know that e to the power of x raised to the power of r is e to the power of x times r, where x and r could be any real numbers. So e to the power of s times Ln of a raised to the power of y can be written as e to the power of x Ln of a times y, which is the same as e to the power of sy times Ln of a. Then, by the definition of a general exponential function, this can be rewritten as a to the power of sy. Let's complete the proof for the third law here. For the fourth law, we try to prove that ab to the power of x equal to a to the power of x times b to the power of x. So we know that ab to the power of x, by the definition of a general exponential function, ab to the power of x can be rewritten as e to the power of x times Ln of ab. Next, by the first law of logarithm, Ln of sy can be written as Ln of x plus Ln of y. So here, Ln of ab can be written as Ln of a plus Ln of b. Next, I can distribute x. If I distribute x, I get e to the power of x times Ln of a plus x times Ln of b. Then, by the first law of exponents, of the natural exponential function, we have that e to the power of s plus y is e to the power of x times e to the power of y. So if there are two terms, I can separate these two terms. We have two terms here, so I can separate these two terms. I get e to the power of Ln of a, e to the power of x times Ln of a times e to the power of x times Ln of b. Then, by the definition of a general exponential function, e to the power of x times Ln of a, that's a to the power of x. E to the power of x times Ln of b, that's b to the power of x. So ab to the power of x is a to the power of x times b to the power of x. That completes the proof for the fourth law. Next, let me introduce the derivative of the general exponential function. Let a be a positive real number, and let f of x be the general exponential function a to the power of x. How can we take derivative for this function? Here, in order to take derivative, I can first of all apply Ln to both sides. I get Ln of f of x equal to Ln of a to the power of x. On the right side, when we have Ln to the power of a to the power of x, by the third law of logarithm, says when we have Ln of x to the power of r, I can always bring r to the from for all real number r. So here, for ln of a to the power of x, I can always bring x to the from for all real number x. So ln of f of x is x times ln of a. Next, I can take derivative on both sides. On the left side, if I take derivative, I get 1 over f of x times f prime of x by chain rule. On the right side, ln of a is a constant. So when we take derivative for x, I get 1. So I get 1 times ln of a. Constant multiple stays the same. So I get 1 times ln of a. ln of a is a constant. That's a constant multiple. When we take derivative, the constant multiple stays the same. Next, we try to solve the equation for f prime of x. So I can multiply both sides by f of x. So I have ln of a times f of x. Multiply both sides by f of x. And we know that f of x is a to the power of x. So keep in mind that the derivative of a to the power of x is always ln of a times a to the power of x. Next, let me introduce the graph of the general exponential function. Let a be a positive number, and let function f be the general exponential function a to the power of x. Since a is greater than 0, there are 3 cases. Either a is between 0 and 1, a equal to 1, or a is greater than 1. There are 3 cases. Either a is between 0 and 1, a equal to 1, or a is greater than 1. When a equal to 1, f of x equal to 1 to the power of x, which is 1. That's a horizontal line going through 1. So we don't consider this case. We only consider a is greater than 1 and a is between 0 and 1. Let's consider these 2 cases. A is greater than 1 and a is between 0 and 1. Case 1. If a is greater than 1, then ln of a is greater than 0. If a is greater than 1, then ln of a is greater than 0. The natural logarithmic function looks like this. If a is greater than 1, the natural logarithmic function is greater than 0. If a is greater than 1, the natural logarithmic function is greater than 0. So if a is greater than 1, ln of a is greater than 0. Let's take a limit first. Consider this limit. What's the limit when s goes to net infinity? F of x is a to the power of x. And we know that by definition of the natural exponential function, a to the power of x is e to the power of x times ln of a. When s goes to net infinity, ln of a is a positive number. Net infinity times a positive number is net infinity. That's e raised to net infinity. And we know that for the natural exponential function, e raised to net infinity, that's 0. Which means there's a horizontal asymptote at 0. Since the limit when s goes to net infinity is 0, that means there's a horizontal asymptote at y equal to 0. Let's consider another limit. Limit as s goes to infinity. F of x is a to the power of x. Then, by the definition of the natural exponential, by the definition of the general exponential function, a to the power of x is e to the power of x times ln of a. if I plug in infinity for x, Ln of a is a positive number. Infinity times a positive number is positive infinity. E raised to infinity, that's infinity. Next, let's take derivative. If I take derivative for function f, that's Ln of a times a to the power of x. Ln of a here is always positive when a is greater than 1. A to the power of x, by the definition of a general exponential function, that can be written as e to the power of x times Ln of a. We know that Ln of a is always greater than 0, or a is greater than 1. And the range of the natural exponential function is from 0 to infinity. So e to the power of x times Ln of a is always greater than 0. Positive number times positive number is positive, which means f is increasing for all x. F is increasing for all x. If I take the second derivative, Ln of a is a constant. That's a constant multiple, it stays the same. I take derivative from the function a to the power of x. I get another Ln of a times a to the power of x. That's Ln of a squared times a to the power of x. And we know that a to the power of x, by the definition of a general exponential function, a to the power of x is e to the power of x times Ln of a. Perfect square is always greater than 0. Perfect square, Ln of a squared is always greater than 0. The range of the natural exponential function is from 0 to infinity. So e to the power of x times Ln of a is greater than 0. Positive number times positive number is positive, which means f is always concave up. If the second derivative is always positive, function f is always concave up. And since f of x equal to a to the power of x, which is e to the power of x times Ln of a, which cannot be 0, then there are no x-intercepts. F of 0 equal to a to the power of 0, which is 1, which means the point 0, 1 is the y-intercept. Then, based on this information, let's sketch a graph. Horizontal asymptote is y equal to 0. There's no x-intercept. Y-intercept is 0, 1. The graph is always increasing, concave up. The graph is always increasing, concave up. And when x goes to infinity, f of x also goes to infinity. That's the graph of the function f of x equal to a to the power of x when a is greater than 1. Horizontal asymptote is y equal to 0. Case 2, a is between 0 and 1. We know that when a is between 0 and 1, Ln of a is always less than 0. For the natural logarithmic function, when a is between 0 and 1, Ln of a is always less than 0. How can we sketch a graph for the general exponential function? Let's take a limit first. Take a limit for the function f as s approaches to net infinity. And we know that function f is a to the power of x. By the definition of a general exponential function, a to the power of x can be written as e to the power of x times ln of a. When s goes to net infinity, x is net infinity here. ln of a is a negative number. Net infinity times a negative number is positive infinity. And we know that e raised to positive infinity is infinity. Another limit. When s approaches infinity, function f is a to the power of x. By the definition of a general exponential function, a to the power of x, that's e to the power of x times ln of a. When x approaches infinity, since ln of a is less than 0, infinity times the negative number is net infinity. So we get e raised to net infinity. And we know that e raised to net infinity is 0, which means there's a horizontal asymptote at 0. So there is a horizontal asymptote at y equal to 0. Next, let's take derivative. F prime of x, that's ln of a times a to the power of x. We know that a to the power of x, by the definition of a general exponential function, that's e to the power of x times ln of a. Since the range of the natural exponential function is always from 0 to infinity, e raised to x times ln of a is always greater than 0. And we know that when a is between 0 and 1, ln of a is less than 0. Negative number times a positive number is negative. Negative number times a positive number is negative. Since f prime is less than 0, then f is decreasing for all x. Since the derivative is less than 0, f is decreasing for all x. How about the second derivative? If we take derivative again, ln of a is a constant multiple. It stays the same. I take derivative for a to the power of x. I get ln of a times a to the power of x. That's ln of a squared times a to the power of x. And we know that a to the power of x, by the definition of the general exponential function, a to the power of x is e to the power of x times ln of a. Since the range of the natural exponential function is from 0 to infinity, e to the power of x times ln of a is always greater than 0. And also we know that perfect square is always positive. So ln of a squared is always greater than 0. Positive number times positive number is always positive. Since the second derivative is always positive, then we know that f is concave up for all x. Next, we try to find the x and y intercepts. Since f of x equal to a to the power of x, which is e to the power of x times ln of a. Since the range of the natural exponential function is always from 0 to infinity, e to the power of x times ln of a cannot be 0. Since function f cannot be 0, there are no horizontal, there's no x-intercepts. There are no x-intercepts. Since function f cannot be 0, there are no x-intercepts. If I plug in 0 for x, I get a to the power of 0, which is 1. That means the point 0, 1 is the y-intercept. Next, based on this information, let's sketch a graph. Let me put a graph here, so it's easier to compare these two graphs. First of all, there are no x-intercepts. Y-intercept is 0, 1. And horizontal asymptote is y equal to 0. So this line is a horizontal asymptote. Function f is always decreasing and concave up. Function f is always decreasing and concave up. So function f is decreasing, concave up. Decreasing, concave up. And when s goes to negative infinity, function f goes to positive infinity. That's a graph of f of x equal to a to the power of x when a is between 0 and 1. And in both graphs, we can see that the domain of the functions is always all real numbers from negative infinity to infinity. How about the range? In the first graph, function f varies from 0 to infinity, and f is continuously increasing. So the range is from 0 to infinity. For the second graph, function f varies from infinity to 0, and f is continuously decreasing. So also, the range is from 0 to infinity. Range is the set of all real numbers from 0 to infinity. That's the domain and range of function f. Next, let me recall a formula which we learned in section 5.2. In section 5.2, we learned that the derivative of Ln of absolute value of x is always 1 over x for all x not equal to 0. That's what we learned in section 5.2. Also, let me recall the power rule. That's what we learned in the first semester calculus. It says the derivative of x to the power of n always equal to n times x to the power of n minus 1, which says I can always bring n to the front and reduce the power by 1. That's called power rule. That's what we learned in first semester calculus. And this formula is true for all rational number n. Today, we'll prove it. This formula is actually true for all real number n. Today, we'll prove it. This formula is actually true for all real number n. Let's prove it. When we prove this theorem, consider two cases. X. Here, x could be either 0 or not equal to 0. There are two cases. X could be either 0 or non-zero. Let's first of all consider x is 0. Case 1, x equal to 0. If x equal to 0, the left-hand side is derivative of 0 to the power of n. We know that derivative of 0 is 0. So left-hand side is 0. How about right-hand side? Right-hand side is n times 0 to the power of n minus 1. And we know that 0 raised to any power is 0. We get n times 0. N times 0 is also 0. So when s is 0, left-hand side equal to right-hand side. That complete proof for this special case when s is 0. Now, case 2, when s is not 0. We try to use logarithmic differentiation to prove this formula. First of all, let f of x equal to x to the power of n. Since we try to use logarithmic differentiation, but function f or x may be negative, in order to use logarithmic differentiation, we must take absolute value on both sides. Then absolute value of f of x is absolute value of x raised to the power of n. That's the same as absolute value of x raised to the power of n. Next, apply log on the left side and right side. Apply natural log on the left side and right side. So, natural log of absolute value of f of x equal to the natural log of absolute value of x raised to the power of n. Then, by the third law of logarithm, we can bring exponent to the front. I get n times Ln of absolute value of x. Next, we take derivative on both sides. According to this formula, when we take derivative for Ln of absolute value of x, I get 1 over x for all x not equal to 0. Here, since x is not 0, f of x cannot be 0. So on both sides, f of x is not 0, s is not 0. So I can use this formula here. On the left side, if I take derivative, I get 1 over f of x. There's no more absolute value. When we take derivative, there's no more absolute value. I get 1 over f of x. And then by chain rule, times the derivative of an inside function. That's f prime of x. That's the left side. On the right side, n is a constant multiple, it stays the same. If I take derivative for Ln of absolute value of x, I get 1 over x with no absolute value. Then we try to get f of x, f prime of x by itself. I multiply both sides by f of x. So f prime of x is n times 1 over x times f of x. And here we know that 1 over x is x raised to -1. F of x is x to the power of n. Then, by the first law of exponent, a to the power of x times a to the power of y is a to the power of x plus y. We add exponents. When we multiply two numbers with the same base, n exponents. Here we get x to the power of n minus 1 if we add exponent. That completes the proof for the power rule. So the power rule is true for all real numbers, not only natural numbers, it's true for all real numbers. When we take derivative for x to the power n, bring power n to the front, reduce the power by 1. That's true for all real numbers. Next, let me introduce the general logarithmic function. Let a be a positive real number with a not equal to 1. And then the function log base a of x be defined as log base a of x equal to Ln of x over Ln of a for all positive real number x. Then the function f of x equal to log base a of x is called the general logarithmic function of base a. That's how we define the general logarithmic function. Next, let me show you the graph. Let me show you how the graph looks like. Graph of the general logarithmic function. First of all, let a be a positive number with a not equal to 1. And let function f be the general logarithmic function, log base a of x. In order to sketch a graph, let's also consider two cases. Case 1, a is greater than 1. Case 2, a is less than 1. Consider two cases. A is greater than 1 or a is less than 1. Case 1, a is greater than 1. If a is greater than 1, then we know that Ln of a is positive. How can we sketch the graph? Let's take a limit first. How can we take a limit as s approaches to 0 from the right side? We know that the domain is from 0 to infinity because s is a positive real number. So domain is the interval from 0 to infinity. When s approaches to 0 from the right side, f of x is log base x of x, log base a of x. By its definition, that can be written as Ln of x over Ln of a. The denominator is a positive number. If I plug in 0 to the numerator, Ln of 0 from the right side is net infinity. Net infinity divided by a positive number is net infinity. Net infinity divided by a positive number is net infinity. So when s approaches 0 from the right side, the limit is net infinity. That means there is a vertical asymptote at s equal to 0. another limit. Or if s approaches to infinity, what do we get? F of x is log base a of x. And we know that log base a of x is ln of x divided by ln of a. If I plug infinity for x, ln of infinity is infinity. ln of a is a positive number. Infinity over a positive number is positive infinity. Also, function f is log base a of x, which can be written as ln of x over ln of a. That's the same as 1 over ln of a times ln of x. Since ln of a is positive, 1 over a positive number is also positive. So f of x equal to a positive constant times the natural logarithmic function. Since we know the graph of a natural logarithmic function, that's the graph of the natural logarithmic function. Since we know the graph of a natural logarithmic function, we can graph function f using function transformation. When we multiply a function by a constant, by a positive constant, we either stretch or shrink the function, the graph, vertically by the factor of 1 over ln of a. So we shrink or stretch this graph by the factor of 1 over ln of a. When we stretch or shrink the function vertically, when we stretch or shrink the graph vertically, the shape of the graph stays the same, and the s-intercept stays the same. And we know that when s goes to 0 from the right side, the limit is negative infinity. So when s goes to 0 from the right side, the limit goes down to negative infinity. When s approaches infinity, function f also approaches infinity. So when s approaches infinity, function f also approaches infinity. That's the graph of the function y equal to log base a of x when a is greater than 1. And since this function is defined for all positive number x, the domain is the interval from 0 to infinity. And for the range, we know that on the left side, the limit goes down to negative infinity. On the right side, the limit goes up to infinity. And function f is continuously increasing. Function f is continuously increasing from negative infinity to infinity. So the range is from negative infinity to infinity. That's the graph of the general logarithmic function. Now, case 2. A is less than 1. Case 2, when a is less than 1, since a is positive, a is between 0 and 1. When a is between 0 and 1, ln of a is always less than 0. When a is between 0 and 1, ln of a is always less than 0. In order to sketch graph, let's take limit first. When s approaches to 0, from right side, function f is log base a of x. That can be written as ln of x over ln of a. We know that for ln of x, when s approaches to 0 from right side, the limit on the top is negative infinity. On the bottom, since ln of a is less than 0, we have negative infinity over a negative number. Negative infinity over a negative number, double negative is positive. So the limit is positive infinity. Negative infinity over a negative number, double negative is positive. So the answer is positive infinity. And when s approaches to infinity, function f is log base a of x. that can be rewritten as ln of x over ln of a. We know that when x approaches to infinity, ln of infinity is infinity. On the bottom, ln of a is less than 0. Infinity over a negative number is negative infinity. So when x approaches to infinity, f of x approaches to negative infinity. Here, when x approaches to 0 from the right side, if the limit is infinity, that means there is a vertical asymptote at s equal to 0. When x approaches to 0, if there's infinity, if the limit is infinity, that means there's a vertical asymptote at s equal to 0. Also, function f is log base a of x. That's ln of x over ln of a. That can be rewritten as 1 over ln of a times ln of x. Since ln of a is less than 0, 1 over ln of a is negative. So f of x equal to a negative constant times the natural logarithmic function. Since we know the graph of the natural logarithmic function, we can graph function f using function transformation. So here, function f equal to a negative constant times ln of x. Let me sketch the graph here. Since f of x equal to a negative constant times the natural logarithmic function, I first of all flip the graph over the x-axis. Then shrink or stretch the graph by the factor of negative 1 over ln of a. So the graph looks like this. When I flip the graph over the x-axis, x-intercept stays the same. When we stretch or shrink the graph vertically, x-intercept also stays the same. So in both graphs, x-intercept is 1. Now, look at the limit here. When s approaches to 0 from the right, limit is infinity. So when s approaches to 0 from the right, limit go up to infinity here. When s approaches to infinity, the limit approaches to negative infinity. Here, when s approaches to infinity, the limit approaches to negative infinity. So on the other side, the function goes down to negative infinity. That's the graph of the function y equal to log base a of x, when a is between 0 and 1. And then we know that by the definition of the natural logarithmic function, by the definition of a general logarithmic function, the domain is the set of all positive numbers. So the domain is from 0 to infinity. For the range, we know that when s approaches to 0 from the right side, it goes up to infinity. When s approaches to infinity, function f goes down to negative infinity. And here we can see that function f is continuously decreasing. Function f is continuously decreasing. So the range is from negative infinity to infinity. That's the graph of the general logarithmic function. Next, let me introduce a theorem. Let a be a positive real number with a not equal to 1. Then functions f of x equal to a to the power of x and g of x equal to log base a of x. They are inverses of each other. So this theorem says the general exponential function of base a and the general logarithmic function of base a, they are inverse functions of each other. Let's prove it. In order to prove function f and g, they are inverses of each other, we first want to show that domain of function f is the same as range of function g, and the domain of function g is the same as range of function f. So let's find their domain and range first. For function f, since f is the general exponential function of base a, its domain is the set of all real numbers from negative infinity to infinity. And its range is the set of all positive real numbers from 0 to infinity. For function g, since g is the general logarithmic function, its domain is the set of all positive numbers from 0 to infinity. And its range is the set of all real numbers from negative infinity to infinity. And here we can see that domain of function f equal to the range of function g, and domain of function g equal to the range of function f. So domain of function f equal to the range of function g, and domain of function g equal to the range of function f. Next, in order to show function f and g are inverses of each other, we try to show that f of g of x equal to x for all x belong to the domain of function g, and g of f of x equal to x for all x belong to the domain of function f. We try to show these two equations. So let's prove it. Then we verify the first equation first. We try to show that f of g of x equal to x for all x in the domain of function g. F of g of x equal to f of g of x. Here, g of x is log base a of x. For f of log base a of x, I plug this into function f. I get a to the power of log base a of x. I plug log base a of x for x. That's what I get here. I try to prove this is x. So, by definition of a general exponential function, this expression can be written as e to the power of log base a of x times ln of a. By the definition of a general exponential function, a of x is e to the power of x times ln of a. Then log base a of x, by the definition of a general exponential, by the definition of a general Logarithmic function, log base a of x can be written as ln of x over ln of a times ln of a. Here we can cancel ln of a. What's left is e to the power of ln of x. Since e and ln are inverse function of each other, then by inverse function property they get cancelled. What's left is x. So here we verify that f of g of x equal to x for all x in the domain of function g. Next, let's verify that g of f of x equal to x for all x in the domain of function f. Here, g of f of x, that's the same as g of f of x. Function f is a to the power of x, so you get g of a to the power of x. Then for g of a to the power of x, I plug in a to the power of x for x in function g. I get log base a of a to the power of x. This can be written as, by the definition of a general Logarithmic function, this can be written as ln of a to the power of x over ln of a. ln of a to the power of x over ln of a. Then, by the third law of logarithm, I can bring x to the front. So the numerator is ln x times ln of a over ln of a. If I cancel ln of a, what I get is x. So g of f of x is the same as x, equal to x for all x in the domain of function f. Therefore, f and g, they are inverse function of each other. So f and g are inverses. So f and g, they are inverses of each other. Therefore, keep in mind that the general exponential function of base a and the general Logarithmic function of base a, they are inverse function of each other. That's what this theorem says. Next, let me introduce laws of logarithms for general Logarithmic functions. Let a, x, y be positive real numbers with a not equal to 1, and let r be any real number. First law says log base a of x times y is log base a of x plus log base a of y. Second law says log base a of s over y is log base a of x minus log base a of y. Third law says log base a of x to the power r is r times log base a of x. So the first law says we can convert for log base a, I can convert multiplication to addition. For log of base a, I can convert division to subtraction. For log base a of function, even there's an exponent, I can always bring exponent to the front for all real number r. Those are the three properties of the law of logarithms. Let's prove it. How can we prove the first law? First law says log base a of x times y. By the definition of a general logarithmic function, log base a of sy can be written as ln of sy over ln of a. Then, by the first law of logarithm for the natural logarithmic function, the numerator can be written as ln of x plus ln of y. Denominator stays the same. That can be rewritten as ln of x over ln of y plus ln of y over ln of a. Then, by the definition of a general logarithmic function, ln of x over ln of a, that's log base a of x. ln of y over ln of a, that's log base a of y. That's the proof of the first law. Proof for the second law is very similar. Log base a of s over y. By the definition of a general logarithmic function, it can be written as ln of s over y over ln of a. Then, by the second law of logarithmic function for natural logarithmic function, the numerator can be written as ln of x minus ln of y. That's the second law of the natural logarithmic function. Denominator, I leave it the same. That can be rewritten as ln of x over ln of a. Minus ln of y over ln of a. Then, by the definition of a general logarithmic function, ln of x over ln of a, that's log of base a of x. ln of y over ln of a, that's log base a of y. That's a proof of the second law. For the third law, log base a of x to the power r. First of all, by the definition of a general logarithmic function, this can be rewritten as ln of x to the power r over ln of a. Then, by the third law of natural logarithmic function, the numerator can be written as r times ln of x. We can always bring r to the front for all real number r. That's the third law of the natural logarithmic function over ln of a. This can be rewritten as r times ln of x over ln of a. Then, by the definition of a general logarithmic function, ln of x over ln of a is log base a of x. That complete the proof for the third law. So that's a proof for the law of logarithms for general logarithmic functions. Next, let me show you some properties of the general logarithmic function. Let a, b, x be positive real numbers with a not equal to 1. First property says log base a of 1 is 0. We know that log base a of 1, by the definition of a general logarithmic function, that equal to ln of 1 over ln of a. We know that ln of 1 is 0. Since a is not 1, ln of a is not 0. 0 divided by a non-zero constant must be 0. So, log base a of 1 is 0. Second property says log base a of a equal to 1. We know that log base a of a By the definition of a general logarithmic function, log a of base a is ln of a over ln of a. Since a is not 1, ln of a is not 0, so ln of a cancels itself. We get 1. That's the second property. Log base a of a equal to 1. The third property says log base a of a to the power of x equal to x. This is true by the inverse function properties. We know that the general exponential function of base a and the general logarithmic function of base a, they are inverse functions of each other. So if I plug the general exponential function into the general logarithmic function, I get log base a of a to the power of x. They equal to x. So this is true by the inverse function property. The fourth property says a to the power of log base a of x is x. This is also true by the inverse function property. We know that here, since a to the power of x and log base a of x, they are inverse functions of each other. That means if I plug the general logarithmic function into the general exponential function, I get a to the power of log base a of x. They equal to x. So the third property and the fourth property, they are true by the inverse function properties. Also, log base e of x is always the same as ln of x. Log base e of x is always ln of x, because log base e of x, by the definition of a general logarithmic function, that can be rewritten as ln of x over ln of e. We know that ln of e is 1, so you get ln of x over 1, which is the same as ln of x. So log base e of x is always the same as ln of x. Also, there's another special logarithmic function called a common logarithmic function. Common logarithmic function. A log with base 10. A log function with base 10 is called the common logarithmic function. It's denoted by log of x. So for log function, if there's no base, we assume the base is 10. That's called a common logarithmic function. Next, let me introduce the change of base formula. Let a and b be positive real numbers with a not equal to 1. Then log base a of b can be written as log base c of b over log base c of a for all positive real numbers c with c not equal to 1. So this formula says log base a of b can be written as log base c of b over log base c of a. Here I change base from a to c. This formula is called the change of base formula. Next, let's prove it. We know that c is not 1. Since c is not 1, then we know that ln of c cannot be 0. Log base a of b, by the definition of a general logarithmic function, that equal to ln of b over ln of a. Since ln of c is not 0, I can multiply the top and the bottom by 1 over ln of c. I can multiply top and the bottom by 1 over ln of c. So the numerator can be rewritten as ln of b over ln of c. The denominator can be rewritten as ln of a over ln of c. Then, by the definition of a general logarithmic function, the numerator ln of b over ln of c can be written as log base c of b. In the denominator, ln of a over ln of c can be written as log base c of a. Let's complete the proof for the change base formula. And we know that in many calculators, there's only natural log and common log. Natural log is a logarithmic function of base e. Common log is a logarithmic function of base 10. So, in order to calculate log base a of b in a calculator, we must change the base either to e or to 10. So keep it in mind. Note, in order to calculate log base a of b in a calculator, we usually rewrite it as log base a of b. For log a of b, I can change the base to e, write it as ln of e over ln of a. Or I can change the base to 10. So log a of b can be written as log of b over log of a. If there's no base, we assume the base is 10. For ln, we assume it's the log of base e. So then, once I rewrite log in this form, I can use calculator to find the answer. That's how I calculate general log in the calculator. Next, let's look at some examples. Find the value for each of the following expressions and round the answer to 6 decimal places. First example, how do we calculate log base 3 of 2? For log base 3 of 2, we can either change the base to e or to 10. So we can either calculate, write it as ln of 2 over ln of 3, or we can write it as common log of 2 over common log of 3. Then use calculator to calculate this. Either calculate ln of 2 over ln of 3, or log of 2 over log of 3. The answer is the same. We get 0.630930 in the calculator. Round to 6 decimal places. We get exactly the same answer using both formulas. Next example. How do we calculate log base 5 of 7 in the calculator? So we can either change the base to e or base to 10. Log base 5 of 7 can be rewrite as ln of 7 over ln of 5, or common log of 7 over common log of 5. Then use calculator. Both of them give the same answer. In my calculator, I get 1.209062. That's how I calculate general log in the calculator using natural log or common log. Next, let's look at some different examples. Simplify each of the following expressions. First one, log base 2 of 32. How can we simplify this expression? We know that 32 can be rewrite as 2 to the power of 5. And then, by a property of logarithmic function, we know that log base a of a to the power of x equal to x by the inverse function property. Log base a of a to the power of x is x. Similarly, log base 2 of 2 to the power of 5 equal to 5 by a property of logarithmic function. So that's the answer to log base 2 of 32. Next example, how can we simplify log base 3 of 81? We know that 81 can be rewrite as 3 to the power of 4. Then, by a property of logarithmic function, we know that log base 3 of 3 to the power of 4 is 4. That's the answer to this log. Next example, how can we simplify log base 5 of 1 over 25? We know that in the first example, when the base is 2, I write 32 as 2 to the power of 5. In the second example, when the base is 3, I write 81 as 3 to the power of 4 and then get an answer. Is it possible that I can write 1 over 25 using base 5? In example 3 here, base is 5. Is it possible that I can write 1 over 25 using base 5? We know that 1 over 25 can be rewritten as 1 over 5 squared. That can be written as 5 raised to negative 2. So here, 1 over 25 is the same as 5 raised to negative 2. And then, by the property of logarithmic function, log base 5 of 5 raised to negative 2 is negative 2. Next example. How can we simplify log base 7 of radical 7? Is it possible that I can write radical 7 using base 7? Here base is 7. Is it possible that I can write radical 7 using base 7? We know that radical 7 can be rewritten as 7 raised to 1 over 2. So I can write it using base 7 here. Then, by the property of logarithmic function, log base 7 of 7 raised to 1 over 2 is 1 over 2. That's an answer to this log. Next example. Log base 4 of a. Is it possible that I can write a using base 4? In this log here, base is 4. Is it possible that I can write number a using base 4? It's possible, but it's not easy. It's possible, but it's not easy. So let's try to find an easier way. We know that a can be rewritten as 2 to the power of 3. 4 can be rewritten as 2 to the power of 2. So it's hard to write a using base 4. But 4 and a have a common base, which is 2. I can write both of them using base 2. Then here we can use change base formula. Since they have common base 2, I can use change base formula. Rewrite this as log base 2 of a over log base 2 of 4. Writing a and 4 using base 2 is easier than writing a using base 4. So I change base to 2. Then log base 2 of a. Number a can be rewritten as 2 to the power of 3. From the denominator, log base 2 of 4, it can be written as log 2 of 2 to the power of 2. Then, by the property of logarithmic function, log base 2 of 2 to the power of 3 is 3 on the numerator. Log base 2 of 2 squared is 2 on the denominator. So the answer is 3/2. That's an answer to this log. Next example. Log base 27 of 81. Is it possible that you can write 81 using base 27? Here base is 27. Is it possible you can write 81 using base 27? It's possible, it's doable, but it's too complicated. Here we know that for 81 and 27, I can write both of them using base 3, and that'll be much easier. So here, use change base formula. Change the base to 3, it'll be much easier. So, log base 27 of 81 can be rewritten as log base 3 of 81 over log base 3 of 27. Then we know that 81 can be rewritten as 3 to the power of 4. 27 can be rewritten as 3 to the power of 3. Then, by the property of logarithmic function, log base 3 of 3 to the power of 4 is 4. Log base 3 of 3 to the power of 3 is 3. So the answer is 4/3. That's how we simplify this log. Next example. Log of 1 over a. Log base 1 over a of radical 2. Log base of 1 over a of radical 2. Here you can see that it's hard to write radical 2 using base of 1 over a. But we can try to write both of them using base 2. We know that 1 over a can be rewritten as 1 over 2 to the power of 3. that can be rewritten as 2 raised to negative 3. And we know that radical 2 is 2 raised to a half. So I can change both of them to base 2. It's easier to write both numbers using base 2. I can change of base to 2, change of base to 2. So this log can be rewritten as log base 2 of radical 2 over log base 2 of 1 over a. In the numerator, radical 2 is 2 raised to a half. In the denominator, 1 over a is 2 raised to negative 3. Then, by the property of logarithmic function, log base 2 of 2 to a half is a half. Log base 2 of 2 to negative 3 is negative 3. A half divided by negative 3 is negative 1 over 6. That's an answer to this log. Next example, log base 1 over 27 of the 4 root of 3. Log base 1 over 27 of the 4 root of 3. It's hard to write this 4 root of 3 using base 1 over 27, but we can write both of them using base 3. We know that 1 over 27 can be written as 1 over 3 to the power of 3. That's 3 raised to negative 3. And the 4 root of 3 can be written as 3 raised to 1 over 4. Since it's easier to write both numbers using base 3, I can use change base formula, change both of them to base 3. So I get log base 3 of the 4 root of 3 over log base 3 of 1 over 27. Then in the numerator, the 4 root of 3 is 3 raised to 1 over 4. In the denominator, 1 over 27 is 3 raised to negative 3. Then, by the property of logarithmic function, the numerator is 1 over 4. The denominator is negative 3. 1 over 4 over negative 3 is negative 1 over 12. That's how we simplify this logarithmic function. Next example, how can we simplify log base 3 of 6 minus log base 3 of 4 plus log base 3 of 18? Here, by the law of logarithms, we can see that we can always convert addition to multiplication, combine two logs, convert addition to multiplication, and combine two logs, convert subtraction to division. So I can combine the logs by converting subtraction to division. I have log base 3 of 6 divided by 4 times 18. When we have logs with the same base, we can convert subtraction to division and convert addition to multiplication by combining the logs. Then here, 6 divided by 4 times 18. 6 over 4 is 3/2. 3/2 times 18 is 27. So 6 divided by 4 times 18 is 27. And we know that for log base 3 of 27, let's log base 3 of 3 to the power of 3. Then, by the property of logarithmic function, log base 3 of 3 to the power of 3 is 3. That's an answer to this expression. Next example, log base 2 of 50 minus log base 2 of 10 minus log base 2 of 20. How can we simplify this expression? Here we can see that all these three logs have the same base, base 2. Then, by the law of logarithm, I can combine these logs together by converting subtraction to division, subtraction to division, So we have log base 2 of 50 divided by 10, then divided by 20. That's the same as 50 divided by 10 times 20. 50 divided by 10, and then divide by 20. If we simplify, on the denominator, 10 times 20 is 200. 50 over 200 is 1 over 4. And we know that 1 over 4 can be rewritten as 1 over 2 squared. 1 over 2 squared is the same as 2 raised to negative 2. Then, by the property of logarithmic function, log base 2 of 2 raised to negative 2 is negative 2. So that's an answer to this expression. Next example. How can we simplify the expression 6 to the power of log base 6 of 4? How can we simplify the expression 6 to the power of log base 6 to the power of 4? If these two bases are exactly the same, then by the property of logarithmic function, we know that a to the power of log base a of x is always x. This is true by the inverse function property. A to the power of log base a of x is always x. So if the base is the same, 6 to the power of log base 6 of 4 is always 4. So the answer to this expression is 4. Next example. 2 to the power of 1 plus log base 2 of 5. How can we simplify this expression? Here, by the law of exponents, by the first law of exponents, 2 to the power of 1 plus log base 2 of 5 can be rewritten as 2 to the power of 1 times 2 to the power of log base 2 of 5. Here, 2 to the power of 1 is 2. 2 to the power of log base 2 of 5. Since the base is the same, then by the property of logarithmic function, I get 5. 2 times 5 is 10. That's how we simplify this expression. Next example. 3 to the power of 4 log base 3 of 7. 3 to the power of 4 log base 3 of 7. How can we simplify this expression? When there's a coefficient in front of log, we can always bring the coefficient back as exponent. That's the third law of exponent. That's the third law of logarithm says. When there's a coefficient in the front, we can always bring the coefficient back as exponent. So this expression can be rewritten as 3 to the power of log base 3 of 7 to the power of 4. When there's a coefficient in front of log, we can always bring it back as exponent. And then here, when the base is the same, by the property of logarithmic function, I get 7 to the power of 4. When the base is the same, by the property of logarithmic function, I get 7 to the power of 4. 7 to the power of 4 is 7 squared is 49. 49 times 49 is 2401. That's how we simplify this expression. I get 2401. Next example. 5 to the power of log base 5 of a plus log base 5 of 7. By the first law of exponents, 5 to the power of log base 5 of a plus log base 5 of 7 can be written as 5 to the power of log base 5 of a times 5 to the power of log base 5 of 7. And we know that when the base is the same, log base 5 of a equal to a. Log base 5 to the power of log base 5 of 7 equal to 7. By the property of logarithmic functions. Here, a times 7 is 56. A times 7 here is 56. That's how we simplify this expression. Next example. How can we simplify 6 to the power of log base 6 of 5 minus log base 6 of 10. Here, by the second law of exponents, 6 to the power of these two terms is the same as 6 to the power of log base 6 of 5 over 6 to the power of log base 6 of 10. That's the second law of exponents. 6 to the power of log base 6 of 5 minus log base 6 of 10. I can convert subtraction to division. And then when the base is the same, by the property of logarithmic function, in the numerator I get 5, in the denominator I get 10. 5 over 10 can be reduced as a half. That's how we simplify this expression. Next example. How can we simplify 25 to the power of log base 5 of 3? When the base are not the same, what should we do? How can we simplify 25 to the power of log base 5 of 3? What can we do here? Here we know that 25 can be rewritten as 5 squared. I get 5 squared to the power of log base 5 of 3. Then, by the third law of exponent, it says a to the power of x raised to the power of y is the same as a to the power of s times y. So 5 to the power of 2 to the power of log base 5 of 3 is the same as 5 to the power of 2 times log base 5 of 3. And then when there's a coefficient in front of log, by the third law of logarithm, I can bring the coefficient back as exponent. I get 5 to the power of log base 5 of 3 squared. I can bring the coefficient back as exponent. Then when the base is the same, by the property of logarithm, I get 3 squared. And we know that 3 squared is 9. So this expression equal to 9. Next example. Radical 3 to the power of log base 3 of a. Radical 3 to the power of log base 3 of a. How can we simplify this expression? Here the base are different, they are not the same. What can we do here? We know that radical 3 can be rewritten as 3 raised to 1 over 2 to the power of log base 3 of a. And then by the third law of exponents, when we have 3 to the power of half to the power of log base 3 of a, that's the same as 3 to the power of half times log base 3 of a. Then by the third law of logarithm, when there's a coefficient in front of log, I can bring it back as exponent. So this expression can be rewritten as 3 to the power of log base 3 of a raised to a half. By the third law of logarithm, we can bring coefficient in front of log back here as exponent. Then when the base is exactly the same, by the property of logarithmic function, I get a raised to a half. And we know that a raised to a half is square root of a. Square root of a can be rewritten as 2 square root of 2. That's an answer to this expression. Next example. How can we simplify 1 over 4 to the power of log base 2 of 7? Here the base is not the same. Which first we're trying to rewrite 1 over 4 using base 2. We know that 1 over 4 can be rewritten as 1 over 2 squared. And 1 over 2 squared is 2 raised to negative 2. So first of all, 1 over 4 can be rewritten as 2 raised to negative 2 to the power of log base 2 of 7. Then, by the third law of exponent, when we have 2 raised to negative 2 raised to the power of log base 2 of 7, I get 2 to the power of negative 2 times log base 2 of 7. And then, by the third law of logarithm, when there's a coefficient in front of log, we can bring it back as an exponent. So I get 2 to the power of log base 2 of 7 raised to negative 2. I bring negative 2 back as exponent. When the base is exactly the same, by the property of logarithmic function, I get 7 raised to negative 2. 7 raised to negative 2 can be rewritten as 1 over 7 squared, that's 1 over 49. That's an answer to this expression. Next, let's look at some different examples. Expand each of the following expressions. First expression, log base 2 of 4x cubed, y to the power of 4. How can we expand this expression? By the first law of logarithm, we can always convert replication to addition. So expand this expression, I get log base 2 of 4 plus log base 2 of x cubed plus log base 2 of y to the power of 4. That's the first law of logarithm. Next, for log base 2 of 4, 4 can be rewritten as 2 squared. Leave the rest the same. We know that log base 2 of 2 squared, by the property of logarithmic function, that's 2. Log base 2 of 2 squared is 2. For log base 2 of x cubed, by the third law of logarithm, we can always bring exponent to the front. I get 3 log base 2 of x. By the third law of logarithm, I can always bring exponent to the front. I get 4 log base 2 of y. That's how we expand this expression. Next example, log base 3 of x squared over 9 square root of y times z cubed. Log base 3 of x squared over 9 square root of y times z to the power of 3. How can we expand this expression? By the law of exponents, we can first of all convert division to subtraction. I get log base 3 of x squared minus log base 3 of 9 radical y times z to the power of 3. And then by the first law of logarithm, I can convert replication to addition. I get log base 3 of x squared minus log base 3 of 9 plus log base 3 of radical y plus log base 3 of z to the power of 3. Then, by the third law of logarithm, we can always bring exponent to the front as coefficient. I get 2 log base 3 of x minus log base 3 of 9. 9 can be rewritten as 3 squared. Log base 3 of radical y. Radical y is the same as y to the power of a half. Plus log base 3 of z to the power of 3. So I get 2 log base 3 of x minus log base 3 of 3 squared by the property of logarithmic function equal to 2. Log base 3 of y to a half. By the third property of logarithm, I can bring exponent to the front. It's half of log base 3 of y. For log base 3 of z cubed, by the third law of logarithm, we can bring 3 to the front. It's 3 log base 3 of z. Then for the final answer, we multiply everything together. The final answer here is, let me put it here. I get 2 log base 3 of x, distribute negative sign, minus half of log base 3 of y, minus 3 log base 3 of z, and put a constant in the back, minus 2. Next example, log base 5 of square root of 5ab over c cubed. We try to expand this expression. First step, we can convert division to subtraction. Write it as log base 5 of square root of 5ab minus log base 5 of c cubed. Next, we try to bring exponent to the front. Square root of 5ab can be written as 5ab raised to a half, so I can bring half to the front. I get half of log base 5 of 5ab. And then for the second time, I can bring 3 to the front. I get 3 log base 5 of c. Next, I can convert multiplication to addition. I get log base 5 of 5 plus log base 5 of a plus log base 5 of b minus 3 log base 5 of c. Next, we know that log base 4 of 5 is 1. By the property of logarithmic function, we know that log base a of a is always 1. So here, log base 5 of 5 is 1. If I distribute half, I get half plus half of log base 5 of a plus half of log base 5 of b minus 3 log base 5 of c. That's how we expand this expression. Next, let's look at some different examples. Combine each of the following expressions. As a single log. Combine each of the following expressions as a single logarithm. First example, 3 log base 7 of x minus 4 log base 7 of y plus 5 log base 7 of z. We try to combine this together as a single logarithm. So first step, I can bring the coefficient in the front back as exponent. I get log base 7 of x cubed log base 7 of y to the power of 4 plus log base 7 of z to the power of 5. Next, we can combine log together by converting subtraction to division, addition to multiplication. So we get log base 7 of x cubed divided by y to the power of 4 times z to the power of 5. X cubed divided by y to the power of 4 times z to the power of 5. Here I convert this expression, combine this expression together as a single logarithm. Next example, half of log base 5 of x minus 1/3 of log base 5 of y minus 2. How can we combine this together as a single log? So in order to combine logarithm together, they must have the same base. How can we write 2 in terms of log base 5? By the property of general logarithmic function, we know that for any real number x, I can write it as log base a of a to the power of x. For any real number x, I can write it as log base a of a to the power of x. So Number 2 can be rewritten as 2 log base 5 log base 5 of 5 to the power of 2. So number 2 can be written as log base 5 of 5 to the power of 2. I try to write 2 as log base 5. By the third property of logarithmic functions, we know that any new number x, I can write it as log base a of a to the power of x. So here I write 2 using log of base 5. And then for the rest, I can bring the coefficient back as exponent. I get log base 5 of x to a half minus log base 5 of y to a third. Next, we can try to combine the negative term together first. I get log base 5 of square root of x minus log base 5 of cube root of y plus log base 5 of 25. I group negative term together. Let's convert addition to multiplication. I get log base 5 of square root of x minus log base 5 of 25 times cube root of y. Next, I can convert subtraction to division. I get log base 5 of square root of x over 25 times cube root of y. That's how we combine this expression as a single logarithm. Next example. 2 log base 3 of x minus 5 log base 3 of y minus 1/3 log base 3 of z minus 4. In order to combine everything together, I must rewrite every term with the same log. Here we have log base 3, log base 3, log base 3. How can I write number 4 using log base 3? According to the property of logarithmic functions, we know that for any new number x, I can write it as log base a of a to the power of x. So number 4 can be rewritten as log base 3 of 3 to the power of 4. Then in the first term, I can bring 2 back as exponent. I get log base 3 of x squared. For the second term, I can bring 5 back as exponent. I get log base 3 of y to the power of 5. In the third term, I bring 1/3 back here as exponent. I get log base 3 of z to the power of 1/3. Now they all have the same log with the same base. Next, try to combine them together. First of all, we can group all positive terms and all negative terms together. Here, these 3 terms are negative terms. I can group these 3 negative terms together first. I get log base 3 of x squared minus log base 3 of y to the power of 5 minus plus log base 3 of cube root of z plus log base 3 of 81. Next, inside the parentheses, I can convert addition to multiplication. When I combine log together, I can convert addition to multiplication. I get log base 3 of x squared minus log base 3 of 81 y to the power of 5 times cube root of z. Next, I can convert subtraction to division. When I combine logs, convert subtraction to division. I get log base 3 of x squared over 81 y to the power of 5 times cube root of z. That's how we combine this expression together as a single log. Next, let's look at some different examples. Solve each of the following equations. First equation, log base 2 of x plus 3 is 4. How can we solve this equation for x? In this equation, in order to solve for x, we need to eliminate log base 2 first. How can we eliminate log base 2 here? According to the property of general logarithmic function, we know that a to the power of log base a of x is always x. So in this example, the base is 2. If I apply base 2 to both sides, I get 2 log base 2 of s plus 3 equal to 2 to the power 4. If I apply base 2 on both sides, that's what I get here. And then, by the property of general logarithmic function, 2 log base 2 of s plus 3 is the same as s plus 3. Here I eliminate log base 2 on the left side. On the right side, 2 to the power of 4 is 16. Then I can solve an equation for x. Here s equal to 13. And then for logarithmic function, we have to check the answer. Make sure what we plug in is valid. If I plug in 13 for x, I get 13 plus 3, which is positive. That's valid. For logarithmic function, the domain is always the set of all positive numbers. So if I plug in 13, that's valid. So this solution is valid. Next example. How can we solve an equation? Log base 3 of x plus 1 plus log base 3 of x minus 5 equal to 3. How can we solve this equation for x? First of all, when we see two logs, we can apply law of logarithm. Combine these two logs together first. When we combine two logs, we can convert addition to multiplication. So we get log base 3 of s plus 1 times x minus 5 equal to 3. When we combine logarithm together, we can convert addition to multiplication. Then, in order to solve for x, we need to eliminate log base 3 here. In order to eliminate log base 3, we apply base 3 on both sides. So I get 3 log base 3 of s plus 1 times x minus 5 equal to 3 to the power of 3. Apply base 3 on both sides. Then on the left side, by the property of the logarithmic function, 3 log base 3 can cancel. What's left is s plus 1 times s minus 5 equal to s cubed, equal to 3 cubed. 3 cubed is 27. Then simplify left side. On the left side, if I distribute, I get s squared minus 5x plus x minus 5 equal to 27. Combine like terms, I get s squared minus 4x minus 32 equal to 0. Factor, I get x minus a times s plus 4 equal to 0. Then solve an equation for x. I get s equal to a, s equal to negative 4. Now, for logarithmic function, we have to check the answer. Make sure what we plug in, the solution is valid when we plug in. If I plug in a, in the first logarithmic function, a plus 1 is positive, so that's valid. If I plug in a here, a minus 5 is 3, that's also valid. So s equal to a is a solution to this equation. If I plug in negative 4, what do we get? Negative 4 plus 1 is negative 3. For a logarithmic function, the domain is the set of all positive numbers. We can have negative 3 here. So negative 4 is invalid. This answer must be rejected. If I plug in negative 4 plus 1 is negative 3. For a logarithmic function, domain is always the set of all positive numbers. We can't have negative 3 here. So this answer must be rejected. The only solution is s equal to a. Next example. Log base 5 of x minus 3 minus log base 5 of s plus 1 equal to 1. How can we solve this equation for x? First of all, when we see two logs, we try to combine these two logs together. When we combine two logs together, we can convert subtraction to division. So we get log base 5 of x minus 3 over s plus 1 equal to 1. Next, in order to solve the equation for x, we need to eliminate log base 5 first. In order to eliminate log base 5, I apply base 5 to both sides. I get 5 to the power of log base 5 of s minus 3 over s plus 1 equal to 5 to the power of 1. On the left side, 5 to the power of log base 4 can cancel. What's left is x minus 3 over s plus 1. On the right side, 5 to the power of 1 is number 5. I can write 5 as 5 over 1. Then cross multiply. If I cross multiply, I get x minus 3 equal to 5x plus 5. If I cross multiply, I get s minus 3 equal to 5x plus 5. Then solve the equation for x. I can subtract 5x from both sides. I get negative 4x. Then s3 to both sides. I get a. Solve the equation, s equal to negative 2. Then check the answer. Make sure this answer is valid when we plug in. If I plug in negative 2 here, negative 2 minus 3 is negative 5. For Logarithmic function, the domain must be the set of all positive numbers. So if I plug negative 2, I get negative 5. That's invalid. So this answer must be rejected. If there's only one solution and the solution is rejected, that means there are no solutions. If there's only one solution and this answer is rejected, that means there are no solutions. So if I plug in negative 2 minus 3 is negative 5. For logarithmic functions, we cannot plug in negative numbers because the domain is the set of all positive numbers. So this answer is invalid. It must be rejected. Therefore, there's no solution to this equation. Next example, 2 to the power of 3x minus 1 equal to 6. How can we solve this equation for x? In this equation, x is in the exponent. In order to solve an equation for x, we need to bring x down first. How can we bring x down? Let's first of all apply ln to both sides first. If I apply ln to both sides, I get ln of 2 to the power of 3x minus 1 equal to ln of 6. Next, by the third law of logarithm, we can bring exponent to the front. We get 3x minus 1 times ln of 2 equal to ln of 6. Now I bring x down. I can solve an equation for x. So I can first of all distribute ln of 2. I get 3 ln of 2 times x minus ln of 2 equal to ln of 6. Next, I can add ln of 2 to both sides. I get 3 ln of 2 times x equal to ln of 6 plus ln of 2. Then I can divide both sides by 3 ln of 2. S equal to ln of 6 plus ln of 2 over 3 ln of 2. That's the solution to this equation. For exponential function, the domain is the set of all real numbers, so there's no need to check the answer. Next example, 3 times 5 to the power of 2x minus a equal to 13. How can we solve this equation for x? For this equation, we can first of all try to isolate 5 to the power of 2x first. So I can first of all add a to both sides. I get 3 times 5 to the power of 2x equal to 21. Then I can divide both sides by 3. I get 5 to the power of 2x equal to 7. Next, I can apply ln to both sides. I get ln of 5 to the power of 2x equal to ln of 7. Next, I can bring 2x to the front. I get 2x times ln of 5 equal to ln of 7. Then, in order to get s by itself, I divide both sides by 2 and ln of 5. S is ln of 7 over 2 ln of 5. I divide both sides by 2 ln of 5. I get s by itself. And for exponential function, the domain is the set of all real numbers. There's no need to check the answer. This is a solution to this equation. Next example, 7 to the 2x minus 7 to the power of x minus 12 equal to 0. How can we solve this equation for x? In order to solve this equation for x, let's make substitution here. If I let u equal to 7 to the power of x, then how about 7 of 2x? If I square both sides, u squared will be 7 to the power of x squared. Then, by the first rule of exponent, by the third law of exponent, 7 to the power of x raised to the power of 2. That's 7 to the power of 2x. That's the third law of exponents. So u squared is 7 to the power of 2x. If I substitute, I get u squared minus u minus 12 equal to 0. Then solve the equation by factoring. I get u minus 4 times u plus 3 is 0. Solve the equation. U equal to positive 4, u equal to negative 3, which means 7 to the power of x is 4, since u is 7 to the power of x, and 7 to the power of x is negative 3. We know that the range of exponential function is the set of all positive numbers. The range of exponential function is the set of all positive numbers. So 7 to the power of x cannot be negative 3. This answer must be rejected. There's no solution from here. 7 to the power of x cannot be negative 3. The range of exponential function is always the set of all positive numbers. It cannot be negative 3. So this answer must be rejected. Then solve this equation for x. I can first of all apply ln to both sides. I get ln of 7 to the power of x equal to ln of 4. Then I can bring x to the front. I get x ln of 7 equal to ln of 4. Then I can divide both sides by ln of 7. S equal to ln of 4 over ln of 7. That's the solution to this equation. Exponential function can never be negative. The range of exponential function is always positive. It cannot be negative 3. So this answer must be rejected. There's only one solution. S equal to ln of 4 over ln of 7. Next, let me show you some limits about the general exponential and logarithmic functions. For the general exponential function, the graph looks like this. If a is greater than 0, the graph is increasing from left to right. If a is between 0 and 1, the graph is decreasing from left to right. You can see that here. If a is greater than 1, when s goes to negative infinity, the limit is 0. When s goes to infinity, the limit is infinity. So, when a is greater than 1, for the general exponential function, if s goes to negative infinity, the limit goes to 0. If s goes to infinity, the limit is infinity. On the other hand, if a is between 0 and 1, the graph looks like this. So when s approaches to negative infinity, the limit goes to infinity. When s approaches to infinity, the limit goes to 0. So when a is between 0 and 1, when s goes to negative infinity, the limit is infinity. When s goes to infinity, the limit is 0. And for the general logarithmic function, the limit is very similar. For a general logarithmic function, the graph of a function looks like this. If a is greater than 1, the graph is continuously increasing from 0 to infinity. If a is between 0 and 1, the graph is continuously decreasing from 0 to infinity. So here you can see that if a is greater than 1, when s approaches to 0 from the right, limit goes to negative infinity. When s approaches to infinity, the limit goes to infinity. So for the general logarithmic function, if a is greater than 1, when s approaches to 0 from the right side, the limit approaches to negative infinity. When s approaches to infinity, the limit approaches to infinity. Now on the other hand, if a is between 0 and 1, the graph of the general logarithmic function looks like this. That means when s approaches to 0 from the right, limit approaches to infinity. When s approaches to 0 from the right, limit approaches to infinity. When s approaches to infinity, the limit approaches to negative infinity. So for the general logarithmic function, if a is between 0 and 1, When s approaches to 0 from the right, limit approaches to infinity. When s approaches to infinity, the limit approaches to negative infinity. So keep these formulas in mind. Next, let's do some examples. Find each of the following limits. First limit, x approaches to 3 from left side. 2 to the power of 1 over x minus 3. If we plug in 3 here, 3 minus 3 is 0. This is a limit from left side. That means x is a little less than 3. A number less than 3 minus 3 is negative. So this is 0, but it's negative. 2 to the power of 1 over 0, but it's negative 0. It's 0, limit from left side. 1 over 0, 1 over a very, very small number is infinity. And we know that positive number divided by negative number is negative. That's 2 to the power of negative infinity. Here, base 2 is greater than 1. 2 is in the base, which is greater than 1. This is a general exponential function. When the base is more than 1, if the limit approaches to negative infinity, the limit is 0. So this limit is 0. Next example, limit as s approaches to 0 from right side. 0.7 to the power of ln of x. For ln of x, if s approaches to 0 from right side, ln of x approaches to negative infinity. And we know that 0.7 is less than 1. 0.7 is between 0 and 1. For exponential function with a base less than 1, if the limit approaches to negative infinity, the limit is infinity. When s approaches to negative infinity, the limit is infinity. When the base is between 0 and 1, when s approaches to negative infinity, the limit is infinity. So 0.7 to the power of negative infinity is infinity. Next example. Limit as s approaches to 4. 0.2 to the power of 1 over x minus 4 squared. When s approaches to 4, 4 minus 4 is 0. But this is not exactly 4, so this is not exactly 0 here. We know that every number squared is always positive. So you get 1 over 0, but it's positive, a little larger than 0. We know that 1 over 0, 1 divided by a very, very small number is very, very large. So this is infinity. Positive 1 over positive 0, double positive is positive. So you get negative 2 to the power of positive infinity. This limit here is positive infinity. 1 divided by a very, very small number is very, very large. Positive 1 divided by a positive number is positive. So you get 0.2 to the power of infinity. This is an exponential function with a less than 1. When a is between 0 and 1, when s goes to infinity, the limit goes to 0. So when s goes to infinity, the limit goes to 0. So 0.2 to the power of positive infinity is 0. Next example. Limit as s approaches infinity. Log base of 1/3. Log base 1/3 s cubed plus 1. Log base 1/3 of s cubed plus 1 as s approaches infinity. How can we tell this limit here? If I plug infinity, infinity cube plus 1 is also infinity. We get log base 1/3 of infinity. And we know that this is a general logarithmic function with a between 0 and 1. For the general logarithmic function, if a is between 0 and 1, when the limit goes to infinity, when s goes to infinity, the limit is negative infinity. When a is between 0 and 1, when s goes to infinity, the limit approaches to negative infinity. So this limit is negative infinity. Next example. limit as x approaches to 2 from the right. Log base 2 of x squared plus x minus 6. How can we take limit for this function here? If we plug in 2, 2 squared is 4, 4 plus 4, 4 plus 2 is 6, 6 minus 6 is 0. Is this 0 from left side or right side? So here you can see that x squared plus 6 plus x minus 6. It can be factored as x plus 3 times s minus 2. If I plug in 2, 2 plus 3 is positive 5. If I plug in 2 here, 2 minus 2 is 0. But this limit is from right side. Limit from right side means it's a little larger than 2. A number larger than 2 minus 2 is a little more than 0. And we know that 5 times 0 is 0. Positive number times positive number is positive. So this limit is 0 from right side. So we got log base 2 of 0, limit from right side. This is a general logarithmic function with base larger than 1. This is a general logarithmic function whose base is larger than 1. When the base is larger than 1, when s approaches to 0 from the right, the limit is negative infinity. So this limit is negative infinity. Next example. Limit as s approaches to 3 from left side. Log base of 0.4 of x squared minus 7x plus 12. How can we take a limit for this function? If I plug in 3, 3 squared is 9. If I plug in 3 here, 7 times 3 is 21. 9 minus 21 is negative 12. Negative 12 plus 12 is 0. We get 0 here. But it's a limit from 0. It's a limit to 0 from left side or right side. Let's factor the function first. X squared minus 7x plus 12 can be factored as x minus 3 times s minus 4. If I plug in 3, 3 minus 3 is 0. This limit is from left side. That means a little less than 3. A number less than 3 minus 3 is negative. So it's 0 from left side. If I plug in 3 here, 3 minus 4 is negative 1. If I multiply, 0 times negative 1 is 0. Double negative is positive. So this is 0 from the right side. So for polynomial here, if I take limit, I get 0 from right side. Here I get log base 0.4 of 0 from the right. This is a general logarithmic function with base a less than 1. When base a is less than 1, if s approaches to 0 from the right, the limit is positive infinity. If s approaches to 0 from the right, the limit is positive infinity. So log base 0.4 of 0 from the right side is positive infinity. Next, let me show the derivative of the general logarithmic function. How can we take derivative from the general logarithmic function? Log base a of x. By the definition of a general logarithmic function, log base a of x can be rewritten as ln of x over ln of a. And here we know that ln of a is a constant. So this expression can be rewritten as derivative of 1 over ln of a times ln of x. Since 1 over ln of a is a constant multiple, when we take the derivative, constant multiple stays the same. We take derivative for ln of x. So constant multiple stays the same. We take derivative for ln of x. We know that derivative of ln of x is always 1 over x. So derivative of log base a of x is 1 over ln of a times 1 over x. That's how we take derivative from the general logarithmic function. So keep in mind that derivative of the general logarithmic function, log base a of x, is always 1 over Ln of a times 1 over x. And in general, when we take derivative for log base a of some function of x, if we apply chain rule, I get 1 over Ln of a times 1 over the function here. Then by chain rule times derivative of this function f. Similarly, for exponential function, for the general exponential function, we know that derivative of a to the power of x is ln of a times a to the power of x. In general, when we take derivative for a to the power of f of x, if I apply chain rule, I get ln of a times a to the power of x times f prime of x times the derivative of an exponent. So that's the formula for the derivative of the general exponential and logarithmic function. So keep it in mind. Those are the derivatives of the general exponential and logarithmic functions. So keep this formula in mind. Next, let's do some examples. Differentiate each of the following functions. First example, f of x is x to the power of 4 plus 4 to the power of x. How can we take derivative for function f? We know that for x raised to power 4, we can use power rule. We get 4x cubed. And for 4 to the power of x, this is the general exponential function. When we take derivative, we get ln of 4 times the function itself. That's the derivative of this function. Next example, f of x is x to the power of 4 times 4 to the power of x. When we have two functions multiplied together, when we take derivative, apply product rule. When there are two functions multiplied together, when we take derivative, apply product rule. Product rule says derivative of the first times the second plus the first times derivative of the second. That's ln of 4 times 4 to the power of x. Next example, f of x is 2 to the power of x squared. How can we take derivative for this function? Here we have 2 raised to some power of some function here. If I use chain rule, I get ln of 2 times the function itself, 2 to the power of x squared, times the derivative of an exponent. When we get 2 raised to some function here, we get ln of 2 times the function itself, times the derivative of an exponent. That's the derivative of this function. Next example, f of x is 3 to the power of x times tangent x. here we have 3 to some power of some function here. Apply chain rule. We get ln of 3 times the function itself times the derivative of an exponent. For the derivative of an exponent, we use product rule here. When there are two functions multiplied together, use product rule. Derivative of the first times the second plus the first times the derivative of the second. That's the derivative of this function. Next example, f of x is log base 2 of s squared plus 6. Log base 2 of s squared plus 6. For the general logarithmic function, is in the form of log base a of f of x. This function is in the form of log base a of f of x. So the derivative is 1 over ln of 2 times 1 over the function, the inside function, s squared plus 6 times the derivative of the inside function, which is 2x. That's the derivative of this function. Next example, f of x is log base 6 of s squared sine to the power 4 of x. If we try to take derivative directly, it may be too many product rule, chain rule, may be too complicated. Let's try to simplify first. If we use the law of logarithm, simplify this first, and then take derivative, it may be a little easier. So let's simplify first, and then take derivative. By the law of logarithm, I can convert replication to addition. Function f can be rewritten as log base 6 of s squared plus log base 6 of sine to the power 4 of x. Next, I can bring exponent to the front. I get 2 log base 6 of x plus 4 log base 6 of sine x. Then take derivative will be much easier. If I take derivative, 2 is a constant multiple, stays the same. I get 1 over ln of 6 times 1 over x. When there's a single letter x, that's 1 over ln of 6 times 1 over x. That's the derivative to the first function. For the second function, 4 is a constant multiple, stays the same. When we take derivative for log base 6 of sine x, first of all, it's 1 over ln of 6 times 1 over the inside function. Then by chain rule, times the derivative of sine x, which is cosine x. That's the derivative of this function. Next example, f of x is log base 4 of s squared plus sine to the power 4 of x. For this function, we have addition inside of log, and there's no shortcut. We must take derivative using chain rule. There's no shortcut. We must take derivative using chain rule. So take derivative using chain rule. For general logarithmic function, the derivative is 1 over ln of 4 times 1 over the inside function times the derivative of the inside function, which is 2x plus, let's chain rule here, 4 times sine cube of x. Here we bring power 4 to the front, power go down by 1, become 4 sine cube of x. Then by chain rule, times derivative of sine x. Derivative of sine x is cosine x. That's the derivative of this function. Next example, f of x is 3 to the power of x times log base 3 of x. F of x is 3 to the power of x times log base 3 of x. If we take derivative here, we must apply product rule. When there are two functions multiplied together, we need to apply product rule. So product rule says derivative of the first times the second, derivative of the first times the second, plus the first times derivative of the second. That's 1 over ln of 3 times 1 over x. That's the derivative to this function by using product rule. Next example. F of x is 2x squared plus x to the power of sine x. Here, when we see a function in the form of f of x to the power of g of x, there are two ways to take derivative. First way is we can apply implicit differentiation. We first of all apply ln to both sides. For the first method, I apply ln to both sides. I get ln of f of x equal to ln of 2x squared plus x to the power of sine x. Then simplify the right side. By the law of exponent, by the law of logarithm, we can bring exponent to the front. I have ln of f of x equal to sine x times ln of 2x squared plus x. Then take derivative on both sides. On the left side, if I take derivative, I get 1 over f of x times the derivative of function f, that's f prime of x. On the right side, apply product rule. On the right side, apply product rule. Product rule says derivative of the first times the second plus the first times derivative of the second. That's 1 over the inside 2x squared plus x times the derivative of the inside, which is 4x plus 1. Then simplify. 1 over f of x times f prime of x equal to cosine x times ln of 2x squared plus x plus sine x times 4x plus 1 over 2x squared plus x. Then I can multiply both sides by function f. So f prime of x equal function f times this function here, cosine x ln of 2x squared plus x plus sine x times 4x plus 1 over 2x squared plus x. Then, for the final answer, replace function f with an original function. So the final answer is f prime of x equal to 2x squared plus x to the power of sine x times cosine x times ln of 2x squared plus x plus sine x times 4x plus 1 over 2x squared plus x. That's the derivative of this function. That's first method. For the second method, we first of all rewrite function f, use base e. We first of all use the definition of exponential function, rewrite function f, use base e. So function f can be rewritten as e to the power of sine x times ln of 2x squared plus x. We know that by definition of a general exponential function, a to the power of x can be written as e to the power of x times ln of a. Here I treat this as a, this as x. I get e to the power of x times ln of a. I treat this as a, treat this as x. I get e to the power of x times Ln of a. So first of all, I rewrite function for the second method. I first of all rewrite function f use base e by definition of the general exponential function. Next, take derivative from this function. When we take derivative, this is exponential function. So I first of all copy the function e to the power of sine x times Ln of 2x squared plus x, then times the derivative of an exponent. For the derivative of an exponent, we use product rule. Product rule says derivative of the first times the second plus the first times derivative of the second. So for Ln of 2x squared plus x, I do 1 over the inside function times the derivative of the inside function, which is 4x plus 1. Then simplify. After derivative, we simplify. We know that e to the power of sine x times Ln of 2x squared plus x, this is the same as f of x, which is 2x squared plus x to the power of x. So this is the same as original function f. 2x squared plus x to the power of sine x. Then what's inside the bracket? We can simplify. We have cosine x times Ln of 2x squared plus x times sine x times 4x plus 1 over 2x squared plus x. We get exactly the same answer. So using both methods, we get exactly the same answer. Next example, f of x is cosine x to the power of x squared plus 3. So this function is in the form of f of x to the power of g of x. So there are two ways to take derivative. We can either apply Ln on both sides, then apply implicit differentiation, or we can rewrite the function using base e, then take derivative using chain rule. Let me show you both methods here. First method, I first of all apply Ln to both sides. I get Ln of f of x equal to Ln of cosine of x to the power of x squared plus 3. Then, by the law of logarithm, we can bring exponent to the front. We get Ln of f of x equal to x squared plus 3 times Ln of cosine x. Next, take derivative on both sides. On the left side, I get 1 over f of x times the derivative of f of x. On the right side, use product rule. Derivative of the first times the second plus the first times derivative of the second. For Ln of cosine x, I first of all do 1 over the inside function times the derivative of the inside function. Derivative of cosine x is negative sine x. Then simplify. I get 1 over f of x times f prime of x equal to 2x times Ln of cosine x. Here I bring negative sign to the front. I get minus x squared plus 3. If I bring sine to the top, I get sine x over cosine x, which is tangent x. Then, in order to get f prime by itself, I multiply f of x to both sides. I get f prime of x equal to f of x times 2x Ln of cosine x minus x squared plus 3 times 10x. Then, for the final answer, replace f of x with an original function. So f prime of x is cosine x to the power of x squared plus 3 times 2x times ln of cosine x minus x squared plus 3 times tangent of x. That's the derivative of this function. Second method, I can rewrite the function use base e. By the definition of a general exponential function, we know that a to the power of x can be rewritten as e to the power of x times ln of a. Here I treat cosine of x as a. I treat x squared plus 3 as x. So if I rewrite the function using the definition, use base e, f of x can be rewritten as e to the power of x, which is x squared plus 3 times ln of a. Here our a is cosine of x. Then take derivative. When we take derivative for e, I first of all copy the function. I get e to the power of x squared plus 3 times ln of cosine x. Then by chain rule, times the derivative of an exponent. For the derivative of an exponent, use product rule. Derivative of the first times the second plus the first times the derivative of the second. For ln of cosine x, I first of all do 1 over the inside function, then times the derivative of the inside function. Derivative of cosine x is negative sine x. Then simplify. We know that e to the power of x squared plus 3 times ln of cosine x, that's the same as f of x. And we know that f of x is cosine x to the power of x squared plus 3. Times 2x times ln of cosine 3x, cosine x. Here I can bring negative sign to the front, so it becomes minus here. Minus x squared plus 3 sine x over cosine x is tangent x. So I get exactly the same answer as we have here. Using both methods, we get exactly the same answer. That's the derivative to this function. Next, let me introduce the integral of the general exponential function. We know that when we take derivatives for the general exponential function, a to the power of x, we keep the function the same, and then multiply the function by ln of a. When we take the antiderivative, we perform the opposite operation. We keep the function the same. When we take antiderivative for the function a to the power of x, we keep the function the same, then divide the function by ln of a. That's how we find antiderivative for the general exponential function. Next, let's do some examples. Evaluate each of the following integrals. First example, integral of 3 to the power of x dx. This is the general exponential function. When we take antiderivative, we first of all keep the function the same, then divide the function by ln of 3 plus c. That's an antiderivative of this function. Next example, take antiderivative to the function sine x times phi to the power of cosine x dx. This function doesn't look easier. We can find antiderivative directly. So let's think of u substitution. If I let u be cosine of x, then my du is negative sine x dx. We have sine x, we have dx. What's missing is a negative sign. So I can divide both sides by negative 1. I get negative du equal to sine x dx. This function here can be rewritten as phi to the power of cosine x times sine x dx. If I substitute, I get phi to the power of x times phi to the power of u. Cosine x is u. Sin x dx is negative du. Here I can pull out negative sign. I get negative phi to the power of u du. Then apply the formula. This is the general exponential function. When we take anti-derivative, we do 1 over ln of 5 times the function itself. 1 over ln of 5 times the function itself plus c. And then for the final answer, replace u with cosine x. We get negative 1 over ln of 5 times phi to the power of cosine x plus c. That's an antiderivative of this function. Next example. How can we find the antiderivative of the function? Phi to the power of x times sine of phi to the power of x dx. In this function, we are not able to find antiderivative directly, so think of u substitution. In this function, if I let u be phi to the power of x, what's my du? If I let u be phi to the power of x, my du is ln of 5 times phi to the power of x dx. We have phi to the power of x, we have dx. What's missing is ln of 5, but that's a constant, doesn't matter. I can divide both sides by ln of 5. I get 1 over ln of 5 du equal to phi to the power of x dx. Then substitute. Let me rewrite the function first, then substitute. I get sine to the sine of phi x times phi x dx. If I substitute, I have sine of u times 1 over ln of 5 du. Then 1 over ln of 5 is constant, I can bring it outside. I get 1 over ln of 5 times integral of sine u du. Then take antiderivative for sine of u. Antiderivative of sine of u is negative cosine u plus c. Then for the final answer, replace u with phi to the power of x. I get negative 1 over ln of 5 times cosine u. U is phi to the power of x plus c. That's the final answer to this integral. That's the final answer to this integral. Next example. Integral of log base 2 of x over 2x dx. How can we take antiderivative for this function? We are not able to find the antiderivative directly, so think of u substitution. If I let u be log base 2 of x, then my du will be 1 over ln of 2 times 1 over x dx. We have x on the bottom, we have dx. What's missing is 1 over ln of 2, but that's a constant, doesn't matter. I can multiply both sides by ln of 2. I get ln of 2 du equal to 1 over x dx. I multiply both sides by ln of 2. I get ln of 2 du equal to 1 over x dx. Then, let me rewrite the function first. This function can be rewritten as integral of log base 2 of x times 1 over 2 times 1 over x dx. Then I substitute. Log base 2 of x is u. Half is a constant, stays the same. 1 over x dx is ln of 2 du. Then pull out constant, half ln of 2. I get integral u du. Next, take antiderivative. We get half ln of 2 times u squared over 2 plus c. For the final answer, replace u with log base 2 of x. So here, half times this 2 on the bottom is 1 over 4. I get 1 over 4 ln of 2 times log base 2 of x squared plus c. That's an antiderivative of this function. Next example, integral of 4 to the power of x over 2 times 4 to the power of x plus 3 dx. We can find the antiderivative directly from this function. So here, think of u substitution. For u substitution, if I let u be the denominator, I have 2 times 4 to the power of x plus 3. Then du is 2 times ln of 4 times 4 to the power of x. Derivative of 3 is 0. So I get du equal to this times dx. We have 4 to the power of x. We have dx. What's missing is 2 ln of 4. But those are constants, it doesn't matter. I can divide both sides by these two constants. I get 1 over 2 times 1 over ln of 4 du equal to 4 to the power of x dx. This function can first of all be rewritten as 1 over 2 times 4 to the power of x plus 3 times 4 to the power of x dx. Then substitute. The denominator 2 times x to the power 4 plus 3 is u. 4x dx is 1 over 2 times 1 over ln of 4 du. Then pull out constant. If I pull out constant, I get 1 over 2 times 1 over ln of 4 times integral of 1 over u du. Then take antiderivative. I get 1 over 2 times 1 over ln of 4 times ln of absolute value of u plus c. And then for the final answer, replace u with 2 times x to the power 4 plus 3. I get 1 over 2 times 1 over ln of 4 times ln of 2 times x to the power 4 plus 3. In general, we must keep absolute value, but this function is always positive. That's why I change absolute value to parentheses. Exponential function is always positive. 2 times a positive number is positive. A positive number plus 3 is always positive. Since we know what's inside absolute value is always positive, so I can change absolute value to parentheses. Next example, integral of 2 times 4 to the power of x plus 3 over 4 to the power of x dx. How can we take integral for this function? We are not able to find antiderivative directly, so let's try to simplify the function first. This function can be simplified as 2 times 4 to the power of x over 4 to the power of x plus 3 over 4 to the power of x dx, which can be rewritten as 2 plus 3 times 4 to the power of negative x dx. Then we can try to use u substitution. If I let u be negative x, then du is negative dx. We have dx here. What's missing is negative sign, so I can divide both sides by negative 1. I get negative du equal to dx. Then substitute. I get 2 plus 3 times 4 to the power of u times negative du. I can pull out negative sign. I get 2 plus 3 times 4 to the power of u du. Then take antiderivative. When I take antiderivative for number 2, I get 2u. 3 is a constant multiple, it stays the same. When I take antiderivative for 4 to the power of u, that's ln of 4 times 4 to the power of u plus c. Then, for the final answer, replace u with negative x. For the final answer, replace u with negative x. I get 2 times negative x plus 3 times ln of 4 times 4 to the power of negative x plus c. Then distribute negative sign. If I distribute negative sign, I get 2x minus 3 ln of 4 times 4 to the power of negative x plus c. That's an antiderivative of this function.